So in previous videos, we have talked about all these ideas: mutually exclusive, independent, what formulas we can use for and rules or rules if things are or aren't mutually exclusive or independent. All fine, but then the problem comes, we get to a real question: how do we apply these rules? So this is a video where I'll start to talk about applying these rules. First of all, let's just review briefly, again, what do these two terms mean? Mutually exclusive means there is absolutely no way that these two things can appear at the same time. There is a 0% probability of them showing up side by side. These are often used for things of the same category. So for example, if I pull a single card from a deck, pulling a heart and pulling a spade are mutually exclusive, because if I pull only one card, obviously it can only be one suit. It can't be two suits at once. Similarly, if I roll a single die once, the faces of the die are mutually exclusive. When I roll a die once, I can't possibly get more than one face showing. So those are examples of mutually exclusive events. Independent means that finding out the probability of one tells you absolutely nothing about the probability of the other. In other words, the result of one outcome has absolutely no influence whatsoever on the result of another. Now, a few considerations about these. First of all, the conditions of mutually exclusive and independent are not common with people situations. They're more common with dice, coins, cards, etc. What do I mean by that? Well, if you think of the categories into which we put people, we can categorize people by their religion, by their political party, by their race, by their gender, etc., etc., etc. These are big, messy categories. We can't really say that any one category is mutually exclusive with any other. We can't say that any one category is independent of any other. Categorizing people turns out to be a very messy business, because there are always those exceptions. There's people that are odd combinations of things. They're this political party, but they happen to be that religion, that sort of thing. Just human beings are just very quirky, and there are always exceptions to patterns. And therefore, these nice, neat distinctions of mutually exclusive or independent, they're almost never true when we're talking about classifying people. They work much better when we're talking about very simple, inanimate objects. So again, dice, coins, cards, these are the types of scenarios where we're actually going to be using the ideas of mutually exclusive or independent. Another big idea just to keep in mind, whenever you see the words without replacement, processes that involve those words without replacement automatically are never independent. Well, what do I mean by that? Well, suppose we're choosing cards from a deck without replacement. Well, when I pick the first card, all right, then I can figure out the probability that that card is a certain suit or something like that. But then when I go to pick the second card, now instead of 52 cards, there are only 51 cards, because one has been picked already and it hasn't been replaced. So now picking a card out of a deck of 51, that's going to be a different probability than picking a card out of a deck of 52. And in particular, what I pick on the first deck. For example, I want to know the probability of picking hearts. If I pick a heart on the first draw, well, that's going to change the probability of whether I pick a heart on the second draw. And so without replacement, the different draws are going to always have influence on one another, and therefore they're never going to be independent. So that's just a handy trick to remember. When you see the words without replacement, you're not going to be using any of the independence rules. Okay. Let's look at a hard problem. In a certain game, in phase 1, you flip one coin as many as 3 times. If you flip 3 tails, you lose. You automatically lose. As soon as you get your first head in phase 1, you advance to phase 2. In phase 2, you roll a 6-sided die once. If you roll a 6, you win. For any other roll, you lose. What is the probability of winning? Now, of course, if this were an actual test question, we'd have to have answer choices. We're just going to treat this as a calculation here. You may want to pause the video here and attempt this problem on your own, just to get a sense of it. So this is my abbreviation scheme for the problem. In phase 1, we're going to have up to 3 coin tosses. If I toss tail, 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 I lose. As soon as I get the first head, either on the first toss or the second toss or the third toss, then I advance to phase 2. Phase 2 just consists of a single roll of one die. If I roll a 6, I win. If I roll anything else, I lose. So first of all, notice that we're working with coins and dice. Again, very simple things. Whatever I do with the coins is going to have absolutely no effect on what happens with the die. The die roll clearly is going to be independent of the coins. And what this means is that phase 1 is independent of phase 2. So probability of winning, this is the probability of phase 1. What we get is the advance to phase 2. That's how I'll abbreviate it. And in phase 2, we roll a 6. Okay? That is a scenario that will result in winning. And because the two phases are independent, we can multiply these. So phase 1 results in advancing to phase 2 times the result in phase 2 is roll of a 6. Well, one of those factors is very easy to figure out. When you roll one die, what's the probability of getting a 6? Well, that's a probability of 1/6. So that means if we could figure out the first one, the probability that phase 1 results in advancing to phase 2, we would just multiply this by 1/6. So in a way, we're kind of halfway done with the problem. Now let's go and look at phase 1 in a little more detail. Let's think about the outcomes here. If I flip a head, then I advance. If I flip tail and then head, then I advance. If I flip tail, tail, head, then I advance. If I flip tail, 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 then that's no good. Then I'm out. And I want to figure out the probability of that, and a direct calculation of that would be a little bit tricky. Notice that those three cases would have 3 different probabilities because they involve a different number of tosses in each case. But notice that of the 4 possibilities, 3 of them are the thing that I want, and 1 of them is not the thing that I want. This is an ideal scenario for using the complement rule. So the probability of advancing on phase 1 is 1 minus the probability of losing. Of course, the probability of losing is the probability of flipping 3 tails in a row. Well, what's the probability of flipping 3 tails in a row? Well, tail, end tail, end tail, that would be 1/2 times 1/2 times 1/2, which is 1/8. And so the probability of advancing would be 1 minus 1/8, which is 7/8. That is the probability that in phase 1 we wind up advancing to phase 2. So that's our first factor here. So we get 7/8 times 1/6, and this turns out to be 7/48. And this is actually the probability of winning the game. Now this problem here is probably a notch or 2 harder than anything you're going to see on the test, but it demonstrates the basic principles, dividing the problem into stages, and at each point analyzing, are things independent, are things disjoint, and can we use the complement rule to simplify? All of these are strategies that will help you analyze probability questions.